We've now established a way of doing regular convolution with the FFT, even though the underlying effect of convolution with the FFT is circular convolution. To distinguish them, we'll call one linear convolution and the other one circular convolution. So now we're going to go into the actual computation savings a little bit later, but as a broad stroke, we know that to compute all the convolution outputs, if we have a sequence of length n and a sequence of length m, is going to be n times m. But if we're doing this with an FFT, it's possible to actually reduce the total number of computations. However, of course, computing the FFT takes computation itself, and we find that this computation increases, of course, with the length of the sequence. And if we had a very long sequence and x and a very short sequence h, something like this, then if we're going to compute the output via the FFT, we're going to have to take the FFT of length nx, the length of x, of both x and h. And that just seems like wasted computation. It turns out that for a variety of reasons, the fact that we don't want to have to take FFTs of great lengths just to do this type of convolution being one reason. Another reason is perhaps x is infinite length. We really can't, in other words, it's ongoing. Picture, for example, some sound system where the audio comes in and just keeps coming in, and we have to process it and send it back out. In such a situation, you don't want to wait for the whole CD to play, or the whole song, or the whole concert to be over, whatever it might be, before we can actually compute the convolution. We would like to be able to compute the convolution as the data comes in. For these reasons, we're going to explore block convolution. In block convolution, we divide our input into short segments. We compute the convolution of each segment output, and then we combine the outputs of this all together. As a result, we can now use, for the convolution of our small segments, the FFT convolution, or we could even do linear for that matter, but for a variety of reasons it's still advantageous. So first, let's introduce some notation. If the big signal is x of n, we're going to number each of these blocks as x with the subscript, and so on and so forth. So n will be on that axis, and we'll define these x sub r to be this way. It's x of n plus rl, where l is the length of the block. For 0 less than n, let's do l minus 1, and otherwise. Okay, so why have we defined it this way? Well, we would like to treat each of these signals, let's say x of 3 of n. We don't want to keep track of the original n as it related back to x of n. So it's just defined from 0 to l minus 1. And then this little function here translates the block into the correct place. So I guess technically we should start at x0 for this. So we'll have that out there. Okay. Writing that, we now have that x of n is equal to the sum of all our segments. Now when we're building x of n, we have to shift them back into position. So we have this minus RL in there. So everything else is just a straightforward application of what we already know. We have h convolved with x is going to be h convolved with our new representation of x, and since convolution is a linear function and we just have a sum here, we can just write that as the sum from r equals 0 to infinity of h of n convolved with xr n convolved with delta n minus RL. We will call this quantity yr of n, and of course if we take all of it together we would get yr of n minus RL. So the output is just the sum of the individual convolutions. Well, great. The only issue that we have now is we have to deal with the fact that yr is going to actually be longer than L. And so when we do this sum, we're going to have overlap.